All right, number 7. If there are on average 12 buses per hour arriving at a bus stop, find the probability that there are more than 6 buses in 30 minutes. Okay, so I'm just going to highlight a few things here. So on average, 12 buses arriving at a bus stop, all right? And we want to find the probability that there are more than 6 buses in 30 minutes. All right. Now remember, 12 buses arrive per hour, which means in 30 minutes, half of those buses will be arriving, which will be 6 buses. But anyway, before I write that down, I'm just gonna I'll try and define the random variable. So I'll say let x be the number of buses in 30 minutes. And like I said, x follows Poisson distribution because we already defined this is 30 minutes. Half of the bus will be arriving. You know, if 12 arrive per hour, that means 6 will be arriving in 30 minutes. So our parameter is 6. All right, since there will be, I'll just say, since there will be 6 buses in 30 minutes. Great. All right. So what are they asking us? Find the probability that there are more than 6 buses. 6 buses. So all that we have to do here is plug this in our calculator. But before we do that, more than 6, that is same as 1 minus probability less than or equal to 6. And like I showed you previously, you can just plug this guy in your calculator. So let's go. 1 minus, looking for the Poisson CDF. Here we go. All right. Our mean is 6. Our x value is 6. And you should be able to get your answer, which is 0.394. 0.394. Good. Number 8. On Sunday mornings, cars arrive at a petrol station at an average rate of 30 per hour. So, average rate of 30 per hour. 30 cars, 1 hour. Assuming that the number of cars arriving at a petrol station follows Poisson distribution, find the probability that in half an hour, 30 cars arrive. So, I'm just going to define our random variable here. So, A, let y be the number of cars arriving in 30-minute interval. So y follows Poisson distribution with parameter 15, because if 30 cars are arriving per hour, that means 15 will be arriving in half hour. So probability that y is equals to 12 cars arriving will be, you just plug that in your calculator, don't have to show you again, 0.0829. Just plug that in your calculator. Use the Poisson PDF function in your calculator to get that. I'm going to move to B. No cars arrive during a 5-minute interval. So I'll say define my new variable. Let x be the number of cars arriving in 5-minute interval. So 5-minute interval, that means that if 30 cars, just gonna try and increase. So if 30 cars uh, arrive in 60 minutes, uh, how many cars would arrive in 5 minutes? So just gonna divide by 12 here, divide there by 12, scale it down, right? And we're gonna end up with 2.5 cars. So which means that the random variable x follows Poisson distribution. So the random variable x follows Poisson distribution with parameter 2.5. All right. So because 2.5 cars arrive in 5 minutes. All right. And if we want to find the probability of 0 cars arriving in 5 minutes, in 5-minute interval, so that will be probability x is equals to 0. And you can plug that in your calculator as well. Use Poisson PDF function in your calculator. So that will be 0.0821. All right. So remember we said Poisson distribution is scalable. So just scale it down in B and you get your answer. I'll move on to C. More than 5 cars arrive in 15-minute interval. So I'll define my new variable. Let Z be the number of cars arriving in 15-minute interval. And like we said initially, 30 cars, 60 minutes. So how many cars will arrive in 15 minutes? And divide by 4, divide by 4. So we can say that 7.5 cars arrive in 15 minutes. So, which implies that Z follows Poisson distribution with parameter 7.5. So if I want to find no more than 5 cars arriving in a 15-minute interval, so more than 5 cars, sorry, arrive in 15-minute interval, that is same as 1 minus probability Z is less than or equal to 5. Okay. If you plug that in your calculator, you'll get 0.759. I've shown you how to plug this in your calculator, so that shouldn't be a problem really. All right. So that's the mathematical process involved. All right. Define the variable, write the distribution, get your answer. Okay. Number 9. The random variable x is Poisson distributed with mean m and satisfies this equation. So what you are going to do is you are going to use the formula that we wrote in the very beginning. And I said this formula is in your formula booklet. Uh, for any Poisson x variable following Poisson distribution, this formula works. Okay, so you're going to use that formula to try and work out this question. For example, when x is equals to 0, I'll have m to power 0, because m is our parameter, e to power negative m over 0 factorial. Um, when x is equals to 1, m to power 1, e to power negative m over 1 factorial. When x is equals to 4, m to power 4, e to power negative m over 4 factorial. When m, yep, that's exhausted, is equals to 0. So what we need to do is to simplify this equation and then find what we need to find. M to power 0 is 1. 0 factorial is 1. So this will be e to power negative m plus m e to power negative m minus m to power 4 e to power negative m over 24 is equals to 0. I'm going to factorize out negative m. So 1 plus m minus m to power 4 over 24 is equals to 0. Now, e to power negative m cannot be equal to 0. E to power any value cannot be 0. So what you're just going to focus on is this guy in the middle here. All right, this is the guy we are going to focus on. So what you're going to say is 1 plus m minus m to power 4 over 24 is equals to 0. Now, to solve for m here, use your graphing calculator. So use your GDC. So I'll show you how to do that. So if you go on to your GDC, go to, okay, I hope this will work. I just need to install something here, Polysmalt. Okay. Okay. So go to Polysmalt apps and then Polysmalt 2. Good. I'm gonna use Polyroot Finder, degree 4 or order 4. Next, coefficient of x to the power 4 will be negative 1 over 24. Coefficient of x cubed, now we don't have any, 0. Squared, nothing, 0. 1 and 1. Great. And then press solve. All right. So we'll end up with m is equals to 3.16, which is positive. That makes sense. Not that one, because that's a complex number. Not that one. And this one here, negative 0. Now, m cannot be a negative. All right? M cannot be a negative. So the only answer that you're going to take here is the positive value of m. M cannot be negative. All right? So m will be equal to 3.1612. All right. So once you have that, we can go ahead and work out question B. Question B is calculate the probability that x is between uh, 2 and 4. Now remember, these are discrete random variables. So this is the same as probability of x is less than or equal to 5 minus probability x is less than or equal to 1. So discrete random variables, remember these are cumulative probabilities, so you have to look at it. X can only take whole number values, all right? Whole numbers. You cannot take decimals. So if you're looking for the probability between 2 and 4 inclusive, that is same as probability x is less than or equal to 4, it's less than or equal to 5, minus probability x is less than or equal to 1. So if we work that out, we'll end up with, hopefully I can plug all this in my calculator. All right, second, variables. Let's go to Poisson CDF. Okay. The mean is 3.1612, x value 5 minus, again, back to Poisson CDF, same mean, x value 1, and then you'll have 0. So you'll have this answer here. Good. Next question. Let x be a random variable Poisson distribution such that probability that x is greater than 3 is equal to that. So I'm just going to write something here. So probability that x is less than or equal to 3 will be complement of that. So 1 minus 0.555, which will be 0.445. So, and we know that x follows Poisson distribution with the parameter m. We don't know what it is, all right? We don't know what parameter m is. So what you're going to do is we'll use the numerical solver. Now, because these are cumulative probabilities, you use Poisson CDF x3. I showed you how to do this. So you can start plugging it in your calculator. And then you'll get m is equals to 3.94. So once you find m is that, so probability that x is less than 3 is same as probability x is less than or equal to 2. Use Poisson CDF function in your calculator, and you should be able to get 0.247. Number 11, final question. A supplier of copper wire looks for flaws before dispatching it to customers. It's known that the number of flaws follows a Poisson probability distribution with a mean of 2.3 flaws per meter. That's important. So mean of that. So let's start by defining our random variable. So for A, because they want us to determine the way that there are exactly two floors in 1 meter. So what we'll do is let x be the number of floors per meter, which means that x follows Poisson distribution with parameter 2.3. So the probability that x is equals to 2, you can just use Poisson PDF on your calculator to calculate that. It will be 0.265. For B, determine the probability that there is at least one floor in 2 meters. One floor in 2 meters. So remember, what we had initially is floors per meter, 2.3 floors per meter. So per 2 meters, we'll scale up. So multiply that by 2, which will be 4.6. That will be our new parameter. Anyway, let's start by defining our random variable. So let y be the number of floors in 2 meters of y. So that means that y follows Poisson distribution in parameter 4.6. Okay, because this is per 2 meters. So the probability that x is greater than or equal to 1 will be 1 minus probability x is equals to 0, right? Which will be, plug that in your calculator, 0.990. And that's it.